Alright, so welcome to this tutorial, DySPAN 2019. I'll be talking about, my name is Junaid and I am from New York University. So I'll be talking about Internet of Things applications and particularly the quote-unquote mission critical ones, and how do we manage resources in the IoT ecosystem to basically enable these mission critical type of IoT applications. So, as you all know, we are now moving from the Internet of Computers to what we call the Internet of Things. And what is different in the IoT is basically everything is getting connected to each other. Instead of just computers talking, we are now connecting all our appliances, all our devices with each other. So basically, it's a very diverse ecosystem. So it involves the interconnection of various different systems together. We know that this sort of interconnection will revolutionize the operation of electronic systems around us today. So basically new paradigms are emerging, such as smart homes, factories, smart buildings, smart cities, and it's bringing a myriad benefits. For example, we are having improved efficiency, we're having autonomous operation, we are having cost reduction, and so on and so forth. So this is really leading to the proliferation of these sort of technologies. So just to give you a glimpse of what the IoT is supposed to do, we know it will play a critical role in the emerging smart cities paradigm. So for example, some applications like smart street lighting systems, livestock monitoring, smart garbage collection. These are some reference examples to sort of give you a glimpse of how this sort of ecosystem will transform the world around us. So imagine we have a smart connected street lights. If they can communicate with each other, they can adjust the brightness for on-demand sort of lighting. They can report faulty lamps. They can make this lighting system more energy efficient and autonomous. Similarly, let's look at a livestock monitoring application. We can track the health and fitness of livestock using IoT sensors and devices. Also, we can block or constrain their movement within a certain location. And imagine in a big city, these sort of Internet of Things sensors and devices can be really useful. Another application, for example, can be smart garbage collection. So if you have sensors and garbage cans which are connected to each other, you can basically plan your collection route efficiently, and you can also improve energy and cost efficiency. So we all know this, that's not the topic of this tutorial. So what I'm going to talk about is basically dissecting what the IoT networks are, what are the components that comprise this, what is mission critical IoT, and what are their requirements, what sort of resources are available in the IoT space, and what are the decision avenues that we can play around and improve the efficiency of our systems. So if you look at it, there are multiple layers as in communication systems. In the IoT space also we have different layers. At the very physical layer, we're facing the spectrum challenge. And this is very relevant to DySPAN, but in any case, spectrum is the first front that you encounter within an IoT ecosystem from the device level. Then comes the network level. When you try to connect devices, you want to construct a network, and there you want to make sure that the resources are being used efficiently. After that, we'll have a short break, but the next topics are, once you have a network, you want to disseminate information over those networks. You want to spread messages, particularly when the environments are adversarial. How do you tackle those sort of challenges? Another very important aspect of the IoT ecosystem is the cloud. So how do you manage cloud computing resources? This will be the topic after the break. And finally, how do we provision resources in a spatio-temporal setting? For example, in a smart city where you have the notion of space, and you also have the notion of time where requests um, come over time randomly, and you want to make sure that your resources are being provisioned adequately. And finally, we'll have some time for question and answers. So let's get started. Any basic IoT sort of architecture looks like this. This is the most basic one, where you have endpoint devices which are connected to some wireless gateway. That gateway connects to the cloud backend, and from the cloud backend, you were able to control these devices using some monitoring dashboards or wireless devices or handheld devices. So let's take a deeper look. So the ecosystem of the IoT comprises of the following components. So you have endpoint devices which include sensors and actuators. Then these sensors and actuators are being controlled by some software or firmware. Then the next part is the communication part, where you have access points, gateways, core networks. So this part is the wireless or wired communication part. Then you have the cloud infrastructure, which is really important. You have cloud server, which is running applications, and then the cloud applications are being controlled by some user devices. And user devices could be smartphones, could be smartwatches, could be digital voice assistants. So this is how the IoT sort of ecosystem looks like. These are the different components that make up the IoT. So now let's try to get to the mission critical part. Traditionally, the notion of mission critical has been used in communications context, where applications involve life risk. That means if the communication is not there, your life is at stake. So basically, you have dire consequences in case of failure, and this used to be widely used in the context of emergency responders, tactical networks, first responders. This term was widely used in the communications context. But what is mission critical in the IoT space? It's something beyond life risk. So I want to make a point here that this mission critical, or MC IoT, as I will refer to throughout this tutorial, is a much broader notion. It means that the applications are required to work as anticipated, without failing, and every time. So for example, smart city applications, wearables, smart homes, and others. All these applications make our life, so we depend on these things for our life. And we want to make sure that these work right every time, and even though their failure does not necessarily have dire consequences, but still they are mission critical in the broader sense. One more thing I want to emphasize here is the on-demand part. So once you have this IoT ecosystem, there's something called the on-demand service request. That means it is requested whenever you need. Just like we have Uber or 911 requests, they are on-demand services. They are different from something which is either already reserved or pre-allocated. Some examples of mission-critical IoT services are, for example, emergency response systems, public safety systems like fire alarm systems, surveillance, transportation systems, including trains and other transportation networks, especially if they are connected. So some examples of consequences that may happen in a mission-critical IoT ecosystem is, for example, a failed pacemaker, which is connected, could result in a patient's death. If you have a temperature sensor measuring or controlling the boiler's temperature, failure of that sensor could lead to overheating or explosions. Similarly, GPS miscalculation in a mission-critical application could result to an incorrect destination. So even though there is no life risk involved here, but because you failed the mission, you failed the purpose, that's why these applications are mission critical. Another application is failed communication networks in disaster-struck areas. This can have a huge impact in human lives. So bottom line here is that mission-critical IoT applications have stringent design requirements that we need to take care of. So if you want to look at decision avenues or places where we can make decisions and improve efficiency of these networks, they are the following. The first is the endpoint connectivity. What we can change is how we can ensure that there is connectivity for the endpoint devices. So we may have infrastructure-based networks, in which case we want to make sure that the spectrum is being allocated efficiently. If you do not have infrastructure, then you would need other options, for example, device-to-device communications, using unmanned aerial vehicles as base stations to connect these devices. The second avenue is the communication or networking or information dissemination part, where you may need relaying, device-to-device communication, or information dissemination in the presence of persons. Once you have this network and information flowing over this network, you want to access the cloud infrastructure. So the cloud usually has resource bundles involving GPUs, CPUs, memory blocks, and the question is, how do we provision these resources to service requests that may have different complexities? And how do we price these resources so that the revenue of the cloud operator is maximized? And finally, at the top level, we have some system level or policy decisions. For example, in urban applications, where requests are coming from a spatio-temporal sources. So how do we provision resources? Resources in that sense is a very broad term, because you can have first responders, you can have Ubers, you can have even wireless channels as resources that you want to allocate. And finally, we want to make sure that there is security in these networks, even in the resource provisioning part. So the key consideration that we want to look at is, especially in mission critical context, is that mission critical applications require rock solid security. We need to have extreme reliability even in harsh environments. We need to have the ability to operate with little or no human intervention, so we need autonomous operation. And finally, we might need to satisfy requirements that are dictated by industry or government regulations. So overall, if you want to look at the IoT ecosystem, what are the things that really matter? What are the design metrics that we want to make sure are satisfied? So in my opinion, there are three major factors that we consider. First one is the efficiency. That means you want to take care of the quality of service, quality of experience, connectivity, reachability, energy efficiency. So these are some sort of efficiency metrics. Then we also care about economics. That involves pricing allocation, revenue maximization, contract development, payment, refunds. The third most important one is the security and resiliency. So we want these networks and systems to be secure by design. They should be self-organizing, reconfigurable. These are sort of properties that we really desire our systems to have. So now I want to move on to the next part, which is the spectrum management for mission critical IoT. So the endpoint devices, if there is infrastructure already laid down, we want to make sure that the spectrum is available. So let's see what the spectrum challenge really is. So we all know that the number of devices is exploding, and by 2025 it's going to be almost 10 times the number of humans on Earth, which right now is 7.5 billion. So the demand for wireless spectrum is increasing every day. So the problem with this massive surge in IoT devices is that we do not have enough spectrum in our licensed bands. So once we have a large number of these devices, we would not be able to have dedicated spectrum allocation. So what that means is we would have to share spectrum. But the problem with sharing spectrum is that we do not, or we cannot guarantee performance and quality of service or experience. So even though we might have wireless access within the shared spectrum, we cannot guarantee any performance or quality of service or quality of experience. So some solutions that people have looked at to solve the spectrum scarcity problem is using some novel MAC layer schemes to improve efficiency of multiple access. That means you have less and less waiting times to access the spectrum. There has been this cognitive radio technology for long that uses spectrum opportunistically. This is one way to solve the spectrum scarcity problem. Then some people are looking at exploring higher frequencies, for example, millimeter wave channels. This is another way. You do not have enough spectrum. This is one way that you can gain more. But then there are issues associated with each of these. So in this talk, I would want to present something which is a reservation-based spectrum access. So we can use a sub-gigahertz spectrum, but we can implement a reservation-based policy so that you can guarantee performance, but you will have to reserve in advance. And that's where the mission-critical part comes in, because applications can be mission-critical, can be ordinary applications, but because they know their types, they can reserve the spectrum in advance and ensure that they're having the quality of service that they require. So, as I said, spectrum reservation will guarantee performance. It also allows efficient utilization of existing spectrum, and finally, it has the potential for revenue generation by IoT operators. So if the operator has the spectrum and can enforce a reservation-based policy, there's a room for revenue generation. So this is the kind of system model that I'm looking at. I assume that there are devices, and actually they could be a bunch of devices, which communicate with the base station. And the base station has a spectrum reservation chart. It knows which time frequency blocks are allocated to which device. So within those allocated blocks, the device is able to communicate with the base station. And of course, the devices have some contract with the base station in advance, which allows them to reserve this resources. So the IoT devices only communicate with the access points during these designated time frequency blocks. And as I said, they have a contract. So from a operator's point of view, it has, over time, it has certain available frequencies that can be used for allocation. So this is a very abstract picture that I'm putting here. So assuming there are some number of channels for each time available to the operator. For reservation, these channels can be obtained based on some cost. So the average cost of having a channel can be evaluated by simply taking the average of the cost of each time instant. So assuming we know that the average cost of a channel, for obtaining a channel to reserve to an application is kappa, then basically we can offer it to IoT applications. So the challenges here are the access point does not know what type of application is using the spectrum. The other challenge is the utility of spectrum might not be precisely known ahead of time by the application itself. If we treat all of the applications the same way, then it will be kind of lead to a spectrum auction, which is also not efficient in terms of revenue generation. We know in this sort of a setting, the mission critical might be willing to pay more for spectrum reservation than the non-mission critical ones. So what all of this means is there's a need for a dynamic contract that has some advanced payments and can offer you a rebate if you do not want the channel. So the kind of spectrum reservation system that we're proposing is that you reserve the channels in advance, and if you do not need it in the future, you can actually return it and get a refund for your channel. So the kind of setting that we are in is we assume that there's some proportion of devices which are mission critical, and there's the other proportion which is non-mission critical. So the access point offers a menu of contracts to the applications. So eventually this will reveal their true types based on their choices. Whatever they choose will actually reveal their types. So this is the timeline that we're looking at. Initially, applications learn the probability distribution of the utility that they have for spectrum access. Then they enter into some sort of contract. This is kind of the stage one. Once all things are set, we move on to the second stage, when the applications actually learn the utility of spectrum access. At that point, they can decide to either hold or release their spectrum to get a refund. So I try to abstract the mathematical details because they may not be very important, but the idea is, so we want to make sure how we model the utility of the spectrum reservation is based on some physical or some plausible backing or plausible foundation. So we assume that if there was no spectrum reservation, the utility would have been based on how much delay there is in accessing the spectrum due to contention. So assuming that there's exponential sort of delay in a spectrum contention, we can base our utility on that. So let's assume there is some function which depends on the delay. And it's kind of a transformation which does not change the family of distribution of the delay, but it's some transformation of that delay. So assuming we can model that delay, we can have statistics of the delays and utilities. Then, with the assumption that the mission critical applications have higher utility of reserving the channel as compared to non-mission critical applications, we can actually set up a contract. Contract means that we need to find the tuple. That means we need to find the advance payments and rebates for both types of applications. So essentially, we just want to find the P critical, R critical. P critical is the price that the critical application has to pay, R is the refund that the critical application will get if it doesn't use the spectrum. Similarly, for non-critical, we have EN and RN. So once this sort of a menu is offered to the applications, without knowing what their type is, they will select one of them. And that selection will eventually reveal what their type is and will result in some optimal revenue for the operator. So the contract problem can be written as follows. So it's essentially the sum weighted by the proportion of the application types of the revenue that can be generated. So P is the price that you get, refund is, R is the refund, times the probability that you will get a refund, minus the cost of that channel. So if you write a profit maximizing equation, you can actually find out the contract parameters optimally, but there's a caveat here that is that we need to make sure that the mechanism is individually rational. That means that the both type of applications are actually not paying more than what they receive as utility. Another important factor is the incentive compatibility. That means there shouldn't be any incentive for them to hide their true type from the operator by choosing a different contract. So these two constraints, if we put them together with the objective, that kind of forms the optimal contracting problem. And I won't go into the details of how we solve this, but using some property which is called as the first order stochastic dominance, we can actually simplify this problem into a relaxed version, and from there we can find a closed form result for the rebate for the critical application and the non-critical application. Still a fixed point equation here, but we can eventually solve it using numerical methods to find the rebates. Using these rebates, we can actually compute analytically the advance payments that they should make. So, if you simulate this, this is how the prices look like as you change the proportion of mission critical applications. So, one observation is that these are the actual prices, these are the refunds. So the good part is the prices are higher than the refunds. So the difference here is what the operator gains as a result of this contract. Then, if you have a lower advance payment, we notice that there is a lower rebate. An optimal rebate is always lower than the advance payment. If you increase or if you decrease the average utility of the applications, that means that there is lower payment and rebate for non-mission critical applications, and the increase is proportional to the composition of application types. Finally, if the cost of obtaining a channel increases, then the rebates increase, the prices also increase, but the difference reduces. So that tells you that the operator profitability kind of starts reducing. So in this problem, what essentially we have done is we propose a spectrum reservation sort of mechanism that enables critical and non-critical applications to have a reserved spectrum for them, and it can be used on demand. These are the prices that will make sure that this actually happens if the devices or applications have a free choice to pick from. The contract is dynamic, and the optimal and rebates and the payments are obtained analytically. So that kind of gives us some insight into how the spectrum can be managed in a mission-critical IoT ecosystem. This was the first part, but let's get to the second part. Once you have the spectrum, you want to make sure that you actually form a network. So this part is really related to network connectivity, especially if your infrastructure is challenged. That means you do not have the communication infrastructure that is required to connect devices. So let's look at this, where this scenario is where UAVs or unmanned aerial vehicles are being used as base stations to connect ground devices. We know UAVs have been used in a lot of different contexts. For example, drone deliveries, also the military is trying to use them, but the wireless communication industry also is interested in using UAVs for connecting wireless devices on the ground. So the objective of this sort of interconnectivity for IoT is to maximize the coverage and connectivity of remotely deployed mobile interfaces. The second objective is we want to efficiently deploy an overlay network of mobile access points so that they are able to serve the mobile smart devices on the ground. So I'm going to call the access points as maps and the smart devices on the ground as MSDs. The unique challenges in UAV-based communication is that unlike traditional communication infrastructure, we do not have backhaul. That means we do not have optical fiber connecting the base stations, or we do not have microwave-based point-to-point antennas. So if you're having two UAVs, they can only communicate with each other using device-to-device wireless-based communication. But there is no backhaul, which kind of creates a big challenge, especially in a multi-layer scenario. to approach this sort of problem where you want to place UAVs to try to connect devices on the ground, several approaches have been used in the literature. The first one is kind of the facility location problem. It's also called the key median or the K-center problem, where your goal is to identify where to put resource points and such that the devices are able to connect to them with a minimum cost or distance. The problem in this sort of a solution is, first of all, it's centralized. Even though it's centralized, it's going to be hard. Only approximate algorithms are available. There is no guarantee of connected facilities. This is very important for some point here. That means that facilities can be located arbitrarily far from each other. So they, assuming they have wireless interfaces, they may not be connected with each other. And lastly, it requires centralized planning. Another sort of solution that can be done theoretically is this covering of pin packing problem. So assume that you have a set of wireless devices on the ground. You want to overlay UAVs. You could do that in a pin packing fashion. So in this fashion, you will have UAVs placed exactly in the center of these circles. And even though now they can connect to each other, but again, the problem is that it'll be hard. And secondly, doing it for an arbitrary shape is very difficult. So it's not adaptive. It's not adaptive to the network changes. It's again a centralized problem. So what we want to achieve is something like this. We want to have, this is our desired configuration. Assuming we have devices on the ground, which are represented by these blue dots, we want to overlay them with a network of UAVs that is configured in this way. That makes sure, so what is unique about this is, first of all, it makes sure that the devices are appropriately covered, and also the UAVs are connected with each other. So even though there's no backhaul, there's no communication infrastructure, still you are able to relay information among the UAVs to connect something which is spatially dispersed on the ground. And doing this is a non-trivial task. So let's see how we do this. This is an abstraction of this multi-layer network. We have UAVs on the top layer, and we have wireless devices in the ground layer. The UAVs can connect to each other if they are close enough within a certain wireless communication range. Similarly, these UAVs have some coverage region on the ground, and the devices are only able to connect to them if they are within that range. Again, there are some technical details here, but we can represent the connectivity using the adjacency matrix for the maps, the degree matrix of each device, which is a derivative from the connectivity matrix, is referred to as D here. And then this is kind of the cognition loop that we're looking at. The first step is matching between the devices and the UAVs. So the devices connect to its nearest UAV. Then we determine the control input for the UAV. So we decide which UAV goes where. There's some discretization step here, but then we update the position and velocity of the UAV. Finally, we update the goal where the UAV should eventually go to, and this continues again with the next step of matching between the UAVs and the ground user. So if we continue this cognitive loop, this eventually should lead to a framework or a connected configuration that we want, which is also resilient to failures. So as I said, the first step is a matching between UAVs and devices, which is done with some matching function that is dependent on the distance or the L2 norm, which is typically the case in most wireless communication channels. The path loss is generally a function of the distance, and here we just represent it with a generic function phi, And the goal here is that each device tries to connect to the UAV which provides the maximum utility. And there's a gain here because sometimes a device or a physical or a wireless device may have the option to connect to multiple UAVs. So there is a kind of a game here which decides which UAV connects to which map. For the control of the UAVs at the top layer, we use the standard kinematic model where the displacement is integrated to velocity and the velocity is integrated to the acceleration. It's pretty standard robotics model that we use for the UAVs. So our controller essentially looks like this. It has three components. So every UAV is controlled by some control input. With the first part, which represents the gradient-based term that is based on the attractive and repulsive forces between UAVs. Because when the UAVs come together, we want to make sure that they do not collide, so they start repelling each other. But when they go farther away, we want to make sure they're also attracted, so that they stay connected. The second term is a velocity matching. So we want to make sure UAVs try to align their speeds with each other. And the third term is the goal function. Each UAVs should know where it should go, where it wants to reach eventually. So the first attractive repulsive function is kind of is a gradient term. So the VIJs are the gradients that are based on function. This function represents how the signal strength varies as the distance increases. So as we know, as the distance increases, the signal strength tries to drop down. So this is kind of a combination of these gradient terms with the neighbors. The summation is over the neighbors, and there are some details that I won't go into, but these are functions that will make sure that the UAVs try to lock into each other and do not collide. So these are essentially just gains or constant terms that will make sure if the distance is too far, they try to attract each other. If the distance is too close, they try to repel. The velocity matching term is again a linear combination of the difference between velocities. So when we try to minimize this, essentially the UAVs try to tend to stay together. And the final term is the goal function. How do we select the goal? This is kind of a hard thing to do because you typically do not know where the users are in the ground. So here what we're assuming is that at least you know where the cluster centers are. What are the epicenters of the location of the users. This is kind of the minimalist information that we require to set up this system. And those can be obtained using k-means clustering or algorithms of that sort. So we just need these cluster centers that would be set as the goal state for each individual UAV. So let's see a simulation here. So what's happening is the ground users are moving. We start with an arbitrary configuration of the UAVs on the top and implement that. So the UAVs, as you see here, try to come close to each other. They want to go to cluster centers. We have 3 cluster centers here. And each UAV tries to go towards the nearest cluster center, but when it encounters other UAVs nearby, it starts getting repelled and then gets attracted somewhere else. And essentially, it will result in a configuration that covers these ground users on the ground and also make sure that this network is connected with each other. So that way, if spatially dispersed devices want to communicate, they can actually connect to the UAV, and through the network of this UAVs, that information can be relayed to other disconnected parts. Also, if some of the UAVs fail, this framework is very adaptive, so resilient. That means if some of the UAVs arbitrarily fail in the middle, the framework is still able to recover. So for example, here I reduce some, from a connected configuration, I reduce some random failures. Let's see. It's a little bit slow here, but from this connected configuration, arbitrarily some random failure event has occurred, which kind of got the network disconnected. But again, because the framework is running in an outdated loop, it will try to reconfigure itself and then obtain a configuration which is again tries to follow this principles that we laid out to connect the ground users and also stay interconnected with each other. And notice, it's very interesting here that in the middle, because these users are clustered, that means there's a very high density in the centers. So the UAVs at the top tend to be very, very close to each other. You will see like multiple connections here, but when they are, the users are sparse, for example, this cluster, the UAVs covering them also kind of spaced away. I think this will keep running on for a while, but the idea is that eventually it will converge to a configuration which is stable and make sure that we have the desired properties that we want. Okay. So let's move on. Okay, so to measure the performance of this framework that we have, we use the following metrics. First one is what proportion of the devices on the ground are covered. Then we have the probability of information penetration within the maps. So within the UAVs, what is the probability that if I infuse the information, what is the probability that it actually penetrates throughout that network? And then we can actually use frameworks from mathematical epidemiology to actually quantify that analytically. Then finally, there's another metric which is the reachability. That means whether the network of UAVs is connected or not. Because even though it might be overall connected, but there can be an isolation somewhere. That means one UAV might be isolated from the others. That sort of scenarios can be highlighted with a metric that captures the reachability. In our case, we use the Fiedler value. Fiedler value is the second largest eigenvalue of the Laplacian matrix. So in that case, if this value is non-zero, that means the network is connected. The higher this value is, the more connected the network is. So these are some results that we had. This is the time evolution graphs. So as time went on, the probability of coverage of the ground users kept increasing until I infused some failure event, or I simulated some failure at t equals to 10, which immediately dropped the coverage, connectivity, reachability, and using the adaptive framework, it started recovering. These are basically for different percentages of failures. For different failures, the network recovered and eventually went on to a much higher level of connectivity. So this result basically shows how resilient the framework is, at least to random failures. We can't say much about coordinated attacks, but if the failures are uncoordinated, we are able to recover. This figure here shows the reachability. As I was saying, over time, the network was not connected, but at some point, the network immediately got connected, but disconnected again, before finally reaching to a state which is highly connected. So these are metrics that shows how this sort of framework performs in an online manner. I want to also show here some comparisons with competing solutions that other people have provided or the theoretical frameworks provide. For example, the first one, as I mentioned, the circle packing one. If we use that type of approach, we'll have a circle of UAVs. The UAVs are very, very relevant, but they are not covering the entire. They are covering, but basically they should be close in the middle because there's a high density of users in the centers. So one or two or a few UAVs may not be able to provide connectivity to all. Because of these constraints, this is may not be a good configuration in some of those metrics that we laid out earlier. The other approach was the P-median approach. That basically looks at where the demand points are and we put the facilities there. So in this case, all the UAVs were placed exactly on top of the demands. But the problem here is they are not connected with each other. So we only have very localized sort of connectivity. The solution that I propose here is results in this configuration. And desirably it achieves both the properties that I wanted. So this figure shows the comparison results. So if you look at the proportion of devices that are covered, both the circle packing, the P-median and our proposed approach achieve the best. But the circle packing is not able to cover all of the UAVs because of the white spaces that we have. If you look at the reachability, the circle packing has a highest reachability because it has a very regular lattice structure that makes sure that information can be disseminated very quickly within that lattice. But our results still perform comparable. The final one is the probability of information penetration. In that case, we suffer somewhat with the P-median, but still it is comparable. So, in summary, in this work I proposed a cognitive sort of framework that makes sure that multi-layer connectivity is achieved autonomically, that is able to interconnect spatially dispersed devices. And if sufficient number of devices are available, we can guarantee that a high network connectivity will be obtained and there will be resiliency to mobility and device failures. Again, if available overlay devices are enough, then we are able to provide connectivity locally to the devices in each cluster of the underlay network. So we can take a break here for like 20 minutes, and then we can resume with. In the meanwhile, if you have questions, please let us. Yes.
Yeah. So it looks like the solution you have, the UAVs are all on a sort of planar type system, right? So first question, I guess, is there any benefit to having like multi-layers in a hierarchical system where higher up UAVs can serve as sort of a backhaul and then like spread out the connectivity in cases where maybe the devices are not as dense on the ground?
So you're talking about the UAV layer or the ground layer?
UAV layer.
So it can be three-dimensional, right? But then, I mean, it's free to go up and down. But the problem is you need to have a reference. So just like in the horizontal plane, you had a reference that I want to go here. So the UAV try to target that, but if it cannot reach that, it just stays close to that. So same thing. If you have the third dimension, the third degree of freedom, again you should have a reference height. And okay, you want to achieve this target height, but if you cannot, then you just go up or down.
I see.
So it kind of becomes a mix and match of UAVs. But it needs to have some reference. That should be externally provided.
And then the second question relates to the devices themselves. So I guess you're assuming that the devices are broadcasting upward, or that they're able to transmit upwards, right? So
yes.
Not a traditional sort of angular.
Traditional is like
Yeah, so if you do have some traditional devices, they could technically still be connected to the network if you get the angles correct, right? And above it is not. Have you considered something like heterogeneous device types?
I have not considered, but this is a very good point. I think I'm technically assuming that they're omnidirectional. That means kind of in 3D space.
I see.
But generally, I agree this is not true. Antennas have their limitations. There are angles that you just would have. You start experiencing a lot of loss. And also, as you mentioned, if you kind of extend this to a elevation dimension, what starts happening is the ground coverage starts increasing vertically. UAV goes up, this cone becomes bigger. It goes down, the cone, essentially the coverage region starts to get smaller. So this is kind of the third dimension that will come. But it can be made more elaborate. And also, if I did not mention that, but there are many extensions that I was looking at in this framework. It's if you so assuming that these clusters are very, very far apart, then so this configuration will split up also. So you need to have kind of a switch where, or two different mode of UAVs, where some of them just work to connect the two kind of clusters.
Right.
Here everyone is working in a single mode. But these are, I think, all kind of interesting directions that we should look into.
Thank you.
Perfect. Yeah, if you want to have a break, I think we can meet at like 10:20.
Call I have to take, but thank you very much.
No problem.